Let's look at what are the important topics generally covered in computer architecture. So if you start with at the bottom, and here is where we can see that we would talk, when it comes to processors, we will talk about pipelining. And you talk about hazard resolution. When you have pipelining, you look at where the hazards are and you overcome them so that you don't end up with the wrong execution. You look at superscalar design, you look at reordering of instructions, out of order processing, so that you can improve performance, or you're not stalled behind instructions that are waiting for either an output or they're waiting for the memory. You look at prediction. This is a very common thing we study when we come across branches or flow control, when we have to make some decision. You look at speculation. When it comes to multiple threading, we look at speculation, where we can speculate on an outcome and continue execution. Vector processors, DSP. Today we look at GPU, graphic processors, and so on. And then when you go a layer down, you look at the instruction set. There are various ways of analyzing that. Then you go into the memory design, you look at the memory hierarchy. You have the L1 cache, which is the first level cache. You have L2 cache, which is the second level, larger. Today we can even have an L3 cache, right? Up to 6 to 8 megabytes of L3 cache is available. Now, when it comes to memory hierarchy, you would talk about addressing maybe some amount of protection for that. When it comes to the L2 cache, you talk of coherence. The cache coherence is a big problem where you need to make sure that different replicas are consistent in the entire system. You look at the bandwidth, the latency of accessing these values, because L2 caches are generally larger, and the number of cycles that you would take to access a block can increase with the size of the cache. Now, as the number of clock cycles increases, the processor in the meanwhile is waiting, right? It's idle. So it would affect performance. Further, if you go in, you would see the DRAM. Now, the DRAM is your main memory. Today we already have solid state devices. You would look at PCM, which is phase change memory. So there are some emerging technologies that are coming, that are trying to replace the DRAM. Of course, the most of these ideas are to combine these emerging technologies with DRAM rather than to completely replace it, because DRAM is a commodity device, and it's available and it's easy to manufacture. So when you have a commodity device, nobody wants to completely replace it because it's going to be very expensive, right? So when it comes to DRAM, you also have some interleaving or some bus protocol to make sure that you're trying to maximize the performance. You're not paying the penalty in terms of latency. Then, of course, on top of that, you have your disk, your tape. Some of those things probably don't exist today, but the disk is your hard drive, and so on. Continuing into it, when you look at those topics that we saw, they were all confined to uniprocessors. When it goes to multiprocessors, that you have more than one processor, then you also have to talk about the network or the interconnection, right? So in today's multi-cores, which is what we have 4 cores, 8 cores, maybe 16 cores, and so on. We need an interconnection network that connects all these cores. Now, we also need, when you talk about network, we also need some kind of switches, right, and routers, so that the packet that is transmitted by one core is received by another. So we have to have network interface. Then comes the question of what kind of topologies we can connect them. A common topology is a grid, right, like a mesh is what we call it. There will be routing strategies ensuring to make sure that the packet is transmitted and it receives its intended destination in an efficient manner. When you look at the processors themselves, there's also the aspect of shared memory. So you have the memory could be shared among all these processors, such that you do simple load store instructions to load a value from memory or store a value into memory, which would simplify, right? Which would simplify your programming aspect, even though there are multiple processors. So shared memory is a logical way of understanding how we can load and store values from the memory. On the other hand, you have message passing paradigm, which is more of MPI, or message passing interface, is a common language that is used, or a protocol that is used for transmitting packets, where you use different kinds of primitives like send and receive primitives. It's a library on which you can communicate back and forth, but these are, you know, big system calls that are used to write to buffers or read from buffers, and you can transmit values, as opposed to the shared memory, which is more of load store architecture. So it's more like you can continue a uniprocessor code, and you can write that for a multiprocessor code or a multi-core code, and that would be more portable. Today, most of the topics today, emerging topics, are in multiple cores, because we already have more than one core in our system. So here is an interesting way of looking at the computer engineering methodology. So the technology trends generally tell us how, the scaling of your transistors, of your clock, so that we can see how circuits are scaled as we move into the future. And one way of looking at this or analyzing this is to evaluate existing systems for bottlenecks. Right? This is the way you look at it. So you build a system and you look, what are the pitfalls? What are the problems that we are seeing in these existing systems? And are we paying a higher price in memory access, or are we paying a higher cost in executing data-intensive applications? So what you need to evaluate existing systems of bottlenecks is you need benchmarks. So you run certain benchmarks on the existing system and analyze and evaluate what are the problems. Where do you see our problems? Are the problems in integer benchmarks, or are the problems in floating point benchmarks, right? And once you take these benchmarks, you simulate new designs and organizations, because now once you know where the problems are, you try to go to those problems, you try to fix them. Maybe you add more hardware, maybe you parallelize the code, maybe you simplify the code, and you do the new organization on which you run some workloads, right, to see whether the performance benefits is true or not. And you fix the system in such a way that you can see the performance benefits on these newer workloads. And once these workloads are run on the newer systems and you have the performance benefits, you will implement the next generation system, right? This goes for the chip, the layout, and the implementation of it, and they become the newer system. And the newer system also will have some bottlenecks. So you evaluate these existing systems for bottlenecks and run on benchmarks and simulate newer designs. And the cycle keeps repeating. And technology trends keep helping this, right? So as transistors are scaling and as they become smaller, it helps us because we can run these systems faster, right? So as we are able to run faster, we can solve some of the bottlenecks, right, of your system. So for example, one of the ways to look at this is the integer or the floating point benchmarks. Now the floating point benchmarks are generally more expensive. So for example, if you want to do say floating point multiply, one of the ways you would do floating point multiply is you would try to adjust the indices of the operand, the radix of it, and once you do the adjustment, you would do a series of shifts and addition, right? So this would generally consume more clock cycles, right? The whole process is going to consume more clock cycles. What you could do is you could throw in more hardware, you could throw in more resources where you could parallelize this. And once you parallelize some of those components, you can run them faster. And this is what we saw. For example, when Pentium 4 came with some of the results for their benchmarks, you had these integer benchmarks and you had these floating point benchmarks. And floating point benchmarks actually did better than integer benchmarks because of the amount of hardware that were given to it. So if you throw in enough resources, you can speed up a system. There's a cost to it. There's a power to it. There's an area overhead that would that you would require to implement it, but it is possible to make things faster. So in this design, what we are seeing here is the trend is to look what are the bottlenecks in the existing systems, simulate new designs, and from those systems implement the next generation, and for which you will again search for bottlenecks and so on.